question of quantum information theory. Maybe you have some sense of it if you're registered for the course. But I would say that we can address this question by considering what I call the fundamental question of quantum information. Right? And the goal is to address the question, what are the fundamental limits of communication? So it's a pretty broad question, and there's many different facets. Right? If you had asked this question in like 1935, this is the question of Shannon, right? Claude Shannon, the inventor of information theory. And to address this question, he invented information theory, what we now call classical. And then that theory has been immensely useful for modern technology. Right? Like the fundamental theory of data compression, what we use now regularly for transmitting files on the internet. This was developed by Shannon. He phrased it in a particular way, but a way that's of practical import. And the other question that goes along with this is what's called channel coding, or communication over a noisy channel. And again, this is something that is ubiquitous now. It was not understood before Shannon. Right? And so this is the basis of what our cell phones and communication over the internet, et cetera. So then what we're doing here is we're reassessing this question under a quantum lens. So we're incorporating quantum mechanics because we know, I mean, I think there was a sense of it at the time of Shannon, but we know that quantum mechanics is a fundamental physical theory of nature. Right? Everything at bottom is quantum mechanical. So if we want to address this question, we had better incorporate quantum mechanics. And this is what people have done since the 1970s. You can really point to the 1970s in the work of someone named Halevo, Alexander Halevo, who only recently won the Shannon Award of the Information for his pioneering contributions over his lifetime. So with this question, if you look at the book, you'll see there's like 20 different versions of this question. And that's why we have part 2 and part 3 of the book, with each chapter dedicated to a different version of this question. Okay? Because you might be interested in sending ordinary classical data, like ordinary bits. You might be interested in sending information privately, secretly. Of course, we want to be able to do that. And now we live in a world where there are quantum computers. Right? They're not that great, but we hope that one day they will be. I'm optimistic. I hope you are too. It's unclear. And so with quantum computers, you can try to send qubits faithfully over some distance. Or the theory is relevant in a local quantum computer when you want to shuffle qubits from one location of the quantum computer to another. Right? So there's many different versions of this question. And that's what we start addressing in part 2 of the course. Right? Part 1 is dedicated to just building up the fundamentals. You know, we have to, build it up one step at a time. And maybe in some cases, you have to knock down something. if you had a wrong idea about how something works. Knock it down and close it up. So there's a fair amount of background, and that's what we'll be going through. I made a listing of a weekly guideline for what we'll get through. It might be pretty optimistic, but we'll try our best. You know, we'll at least try to touch on a few of the communication tasks. That comes at the end of the course, right? So, okay. But this is really the fundamental question. And to address this question, we have to invent information measures and measures of uncertainty. And these are things like mutual information, similar to what Shannon invented for understanding channel coding, and entropy, which is a measure of uncertainty, ubiquitous in physics, right? So, you know, it's a famous story, but like about how Shannon invented entropy. I'll tell you the story. I mean, maybe something you probably heard it before, but I'll say it in case somebody haven't. Shannon came up with this function of a probability distribution. I'll just write it because it's so important. It's so important it appeared in a movie called Arrival. Did anyone see the movie? Yeah. Did anyone recognize the formula? No. I mean, like it was just there was a whiteboard with like all this magic down. Then in the middle it was circled the entropy formula, right? And so it just like wow, it's that important. Not only is it foundational for technology, but it's in a movie too. So what does this mean? Shannon chose the symbol H for entropy. I don't know why. It conflicts with Hamiltonian physics. I mean, he wasn't really concerned with quantum physics, right? So in physics, we usually denote it by S, but throughout the course, as kind of an homage to Shannon, we use H, right? And that's because in this course, we're going to be taking an information approach. And so I don't know if we will actually ever write down a Hamiltonian. Forgive me. Okay. Anyway, the entropy is a function of a random variable, X, okay? And associated with a random variable is a probability distribution, P of X. So already, this is a bad notation, right? Because the entropy depends on the distribution, not necessarily, it's actually independent of the values that the random variable takes. Nevertheless, this is what we do. So it's defined like this. And this is the formula that he discovered was the fundamental limit of data. So he discovered this, and then he was working in Bell Labs, had some connection to von Neumann, a quantum, famous person in quantum physics and computer architecture. And he asked von Neumann, what should I call this? And he said, well, you should call it entropy for two reasons. First, I invented it 25 years ago, and I called it entropy. Second of all, if you call it that, no one knows what it is. So in any debate, you will have the advantage. That's a famous story. How many of y'all have heard that? Really? All right. Good. Then it's like a new story. Supposedly, it's not clear whether it's true. But it gets retold over and over again. Okay. So this is the question that Shannon asked, and I'll just write it here. The purpose of one of the goals of this lecture will be to talk about this formula as the data compression limit, and we'll make it clear what that means. Okay. So this question was asked by Shannon. You could argue that many people were thinking about this question at the time, but Shannon was the one who really came through and addressed it in a very meaningful way. So the question was addressed by Shannon. In 1948. I think I read that he worked on this paper in secret for like 10 years, right? Working at Bell Labs. I guess just was accumulating more and more over time and kind of working comfortably, I guess, like a government in a laboratory like that. And what he did was he introduced information theory to address this question. And as we said, he didn't incorporate quantum mechanics, even though it had been invented and relatively solidified by 1925, many years earlier. And it was only in the 1970s that Halevo started working on it. And Halevo did some fundamental things. Then Peter Shor tells a story that he heard from Halevo that Halevo stopped working on quantum information theory because his advisors at the time said that this doesn't seem worthwhile to work on. You should turn your attention to the problems that people are more interested in. Well, look at the situation now, right? Now we have classrooms of people learning about quantum information. So it changed, but you know, it took some events for that to happen. I mean, the major thing where things changed was when Shor invented his algorithm for factoring on a quantum computer. Then all kinds of people interested in quantum computing and in quantum information. And in basically looking in many areas of classical computer science and information theory, revisiting those and trying to re-understand them from a quantum perspective. Okay? So now we have things like quantum error correction. You know, that generalizes classical error correction. It's fundamental for the theory of quantum communication and quantum computing. We have quantum cryptography, quantum computational complexity. Each of these things that we get dedicated course. Okay, so Shannon used entropy to quantify uncertainty. So it's, you know, entropy quantifies uncertainty. And we're going to be dedicating at least a week or more to the study of quantum entropy. Okay. And there's different versions of entropy. You can relax. People have also set up basic axioms that an entropy function has to satisfy. Okay? If you then relax one of those axioms, you get Regnier's entropy. So Alfred Regnier invented his version of entropy in 1961, 20 years later. He was a mathematician, but now we know that there's actually like operational significance to the Regnier entropy, that they have a meaning. You could argue a physical meaning and a communication content. And one of the perspectives of this new book is Regnier entropy. So we're going to be studying Regnier entropy, Shannon entropy, von Neumann entropy, how they connect to each other, and their various properties, and how they're useful in communication. Shannon used entropy. He also, this one really you can say is his. I don't think the formula for mutual information came before Shannon. So mutual information, usually written like this. It's a function of two random variables with a joint probability distribution pxy, okay? And again, the notation, when you first look at it, it's a bit misleading, but then it has a certain power to it, and you get used to it, like other forms of flunky notation. But it's defined like this. It's the sum of the individual entropies minus the joint entropy, okay? And we're gonna study that in detail. But the way that you compute this is you have this distribution, you would compute the marginal of this, you sum over y, you get the marginal on x. Plug that into this formula, right? Do the same thing for y, marginalized over x, plug the distribution into this formula. And then the joint distribution, you just plug in here and you sum over x and y, okay? Sometimes it's called common information, but it's a measure of correlations between these two random variables. And it turns out to be related to the fundamental limit of communication over a noisy classical channel. Okay, and we'll make all that precise in what follows. So we'll just write down for now is a measure of correlations. And as an exercise, you could try out if the random variables are independent, distribution is a product distribution. Mutual information will be equal to 0. Okay, that's something you can try out, right? And if there's any correlation whatsoever, the mutual information will be strictly positive. Okay, it turns out that 0 is its lowest value, and but there are upper limits as well that we'll talk about later. Okay. So we have 20 more minutes. So we'll try to get through the concept of data compression and the concept of typical sequence. Oh, there's another famous story. Well, I don't know how famous it is, but there's a story about Shannon's original paper. So he originally submitted to a math journal, and his referee was a famous mathematician named Doob, D-O-O-B, who's a professor at Urbana-Champaign. And well, Doob rejected his paper, thought it was terrible, not rigorous. That's awful. And well, Shannon could say, look at him now, right? So that's encouragement, to keep trying, right? There's another person, Stephen Wiesner, who invented something called quantum money. He recently died just a few days ago. He was Israeli. And his paper, which was the foundation of quantum cryptography, he developed the idea in 1970, I believe, and it was rejected. And eventually published in a computer science news magazine. So this is what happens when people deal with work. And, they're reviewing and they don't know, they just can't tell if something's valuable or not. Right? Whatever rejection. It happens with many original ideas. Okay, so let's talk about data compression. And let's motivate it with an example. So we're going to suppose that there's what we'll call information source. We're going to suppose that it's fully characterized. So the probability distribution of the symbols that are being emitted by the information source is known. Okay? The probability distribution is known. So it's going to emit symbols from an alphabet. Okay, sometimes you'd say letters from an alphabet. So the letters will be A, B, C up to H, G, and H. I'm going to draw the histogram or the probability distribution. Okay, and it's just made up. Particular letters will be indexed here on this horizontal axis, and the probabilities will be on the vertical axis. Okay, and then we suppose, and then there's, you know, the different letters, the different symbols. Okay, the total mass, the total probability mass is 1. It's a probability distribution. So if you sum up all these numbers, they're 1. They're each non-negative, right? It's a probability distribution. And then what we're going to suppose is that if you calculate the sum of these probabilities, it's less than epsilon. What is epsilon? Epsilon is always a small number, okay? Epsilon is always a small number. In this class, it's going to be a number between 0 and 1, closer to 0 than it is closer to 1. All right, and the question is, how should we compress this source faithfully with error probability less than or equal to epsilon. Right? So before addressing this question, let me ask a simpler question. Suppose you wanted to represent the source without error at all. How many bits would you need to represent it? 3, good. 8 symbols, log base 2 of that, 3 bits. Right? So just to be totally clear, we would map A to 0, 0, 0, B 0, 0, 1, da, 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 H to 1, 1, 1. Then we can perfectly represent it. Right? So it's like a binary representation of the source. But suppose that epsilon is like 1 over a trillion, right? Or 10 to the minus 18, whatever, make it very, very small, right? Then it doesn't matter. No one will notice. You know, if you don't represent every symbol faithfully. You know, it's kind of like there's the Earth will be engulfed by the sun before it matters, right? Like, that kind of thing. I actually saw that the Science Institute of Berkeley, there's a conference on computational complexity with that name. All right, so now to address this question, how many bits do we need to represent the source? What are the symbols that we care about? Ones that occur most often? Tell me which ones. H or D, exactly. Which include A and D. His name is AB. So, good. So you would just represent these. And the thing is, the idea is that the source will simply, there's a very low chance that it'll emit these symbols. And so if you just compress these, if you just encode those, then you can compress the source from 8 symbols or 3 bits down to 2. And so you save a bit, right? And so in your storage device, your computer or whatever, you only need 2 bits rather than 3. It's a simple example, but what we're going to see is that the case that Shannon considered pretty much looks like this, but the savings is much more drastic than just a bit. It'll be like, linear number, much larger number. Okay, so the idea is just encode the likely symbols, or what Shannon called the typical symbols. And indeed, you just map A to 0, 0, B to 0, 1, C to 1, 0, and D to 1. And then you forget about the rest. Okay. There are many more schemes for data compression. There's a technique called Huffman coding, very famous, but I'm not going to get into that. You can read about that on your own. So other techniques. Huffman. In fact, there are whole courses on data compression. All right. So if we use these two, then we can address this question. And then, indeed, the scheme would be get the symbol from the source. If it's A, B, C, or D, code it as according to this table. If it's E, F, G, or H, you could just code them all to 0, 0, for example. In those cases, you would make a mistake, but the probability you make a mistake due to this histogram would be less than epsilon. Okay. Good. So let's now talk about the more general case from Shannon's data compression theorem and how the entropy becomes the fundamental data compression limit. All right, so now I'm going to change it to an IID information storage. It's going to emit the sequence X1 through Xn. What does IID stand for? Independent and identically distributed. All right, and the distribution will be this. So I'm already introducing a shorthand that we'll use throughout the course. It's very common in information theory books and literature. X superscript n stands for sequence X1 through Xn. Okay. And then big X superscript n is a random sequence of random variables. Okay. And then we said IID, so what happens to this probability distribution is that it will factor into a product of the same distribution, multiplied n times. So we plug into each probability function the symbol xi. Okay? So when you think of this as you can think of it happening sequentially or like even all at once. the source like sequentially emits x1, x2. And each symbol is chosen from an alphabet, right? So so there's some alphabet chi, right? And that could be the alphabet that we had previously. It could have 8 symbols, right? A through H. That's an example. So pretty general situation. You could certainly question the IID assumption. And part of the whole point of the new book was to look at beyond the IID case. And so that's what we'll be getting into when we delve farther into the book with Shamit. Right. The first thing I want to do is recall the law of large numbers. So LLN, law of large numbers, will denote the, we're going to let F be a function that accepts one of these symbols as an input. And so we're interested in the expectation of a function of a random variable. We're going to pick the function in a particular way later. But this is defined like this. You take the probabilities and then you multiply times the function evaluated at that value. Okay, that's the expectation of the function. And then we can denote the sample mean. So we have a random sequence, right? We can denote the sample mean. I'm going to put a bar over the F to denote that it's the sample mean. And it's a function of the random sequence. And it's the usual sample average or sample mean in any experiment. Okay. So what does the law of large numbers tell us? It says that roughly, as n becomes large, it's very likely that the sample mean will converge to the true mean. Okay, that's one of the basic statements from probability theory. Yeah. Say it again. Central limit theorem is related to this. It's a refinement that we just need to, for the purpose of discussion, epsilon from delta. We will look at particular convergence rates in the laws of large numbers later on. Okay. So what does the law of large numbers state? It says for all epsilon in 0 and 1 and delta strictly greater than 0, and it's very common in the information theory literature to say sufficiently large n. What does this mean? If you've taken real analysis or studied limits before, it just means you take n larger than a certain amount and then the same experience for all n larger than that amount that could depend on epsilon and delta, right? That's what I mean by sufficiently large n. The statement is that the probability that the absolute deviation of the sample mean from the true mean okay. So this right here is the error or deviation between the sample mean and the true mean. We're interested in it being small, that deviation being small, and we want the probability that that deviation is small, we want the probability to be high, okay? So the way you should imagine this is that, I don't know, you can think of it as a competition or something, where someone else picks an epsilon and delta, and then they want this condition to be true. What is the power that you have? You're then allowed to react to that choice and pick an n. Just pick n large enough, and then the statement's guaranteed the whole. Okay. And this kind of thing can be fun to play around with in MATLAB. If you like programming, you can program these random numbers, random sequences, and random functions in MATLAB, and see that it will hold. You need sufficiently many runs to see it. All right, we have 2 minutes left. We are running out of time rapidly. So we're going to close by defining the typical set. The notion of typical sequences. I'm going to tell you the Shannon data compression scheme, and then we'll go into a bit more detail. So the typical set, we'll pick the function f to be negative log of the probability of the symbol x. Okay? And this function is called surprisal. Why is that? For symbols with low probability, you would be highly surprised. The surprisal will be large. For symbols with probability closer to 1, the surprisal will be smaller, closer to 0. And then you have funny things where, like, if the probability of a symbol is 0, then you would be infinitely surprised. That's very striking. Okay. Then we define the typical set to be a set of all sequences such that the deviation between the sample entropy, this is like the sample mean when we pick the function to be this way, minus the true entropy. So all sequences such that the absolute deviation between the sample entropy and the true entropy is less than delta, is small. Okay? So if you run through the law of large numbers, what can we say about the probability that a random sequence lands in the typical set for a sufficiently large n? What can we say? Somebody tell. What is the lower bound of this probability by applying the law of large numbers? 1 minus epsilon. Good. So that's, there's different symbols being used, but you run through the definitions of the symbols, and then you say, oh, okay, it has to be larger than 1 minus epsilon. All right. So then something else you can show, and we'll run through the calculation next time, is that the size of the typical set is exponentially smaller than the size of the set of all sequences. That's going to be the savings from using data compression. And then what we'll show, and I think we're pretty much out of time now, is that if you look at the histogram of the, for all sequences, we're going to divide into 2. This is going to be the typical set. With total probability mass greater than 1 minus epsilon. And this is what we'll call the atypical set. with probability mass less than epsilon. So the scheme for data compression will be, this is it. So since we're running out of time, stop taking notes for now, just listen to this part. Yep. The source will emit a sequence. We'll assume that the source has been fully characterized. We know the distribution. You get the sequence. You can look at it. It's classical. It's not like quantum where if you look at it, you disturb it, right? You just look at it. You do this calculation. Since you know the probability distribution, you can calculate the true entropy according to the formula that we read at the beginning. You calculate the sample entropy. You do this, you compare you calculate the absolute deviation. If it's less than delta, you keep it, right? Because it's in the likely set. If the deviation is larger than delta, then you declare an error, okay? So the scheme for data compression is keep the typical set, discard the rest. That's it. That's the basic idea. But then what you do is you do like an encoding like we did before, right? We took A, we mapped it to 0, 0. We took B, we mapped it to 0, 1. So what you do is you, from the set of typical sequences, you're encoding, it's going to be a biggie, encoding. This is the set of all binary sequences of length n times the entropy. That's the size of the typical set, right? The size of this set is 2 to the n times the entropy. It's essentially the same size as the typical set. So you take your sequence, you find a unique mapping from that sequence to a binary encoding of it. You would then send that over a noiseless communication channel, or you'd store it in your, that's what you'd store in your computer. And then to decode it, you do the inverse mapping. That's the idea, and it turns out that's optimal. And the optimal rate of data compression is the entropy. So the number of bits that you need per symbol. So this is the number of bits, n times h of x per symbol. You divide that by n, because there's n symbols. And the rate of compression is bits per symbol. So it's the entropy. Okay? So that's the basic idea of data compression. Let's stop there. We'll pick up on Wednesday.